I'm going to go through the uneven trajectory problem again. So recall it was about throwing a ping pong ball into a cup. So we have an initial condition, an initial throw, 3 meters per second. That would be the magnitude of the velocity at 60 degrees, which means 60 degrees above the horizontal. So here we have the initial velocity in polar coordinates. And this is an uneven trajectory problem because you can see we're also told that the cup is 0.4 meters, it's 40 centimeters below the level at which we release the ball. So an even trajectory is one that starts at a certain elevation and then ends at the same elevation. This one has to go a little bit lower. That's what makes it an uneven trajectory. So the question is, if you're going to do this, 3 meters per second, 60 degrees, it has to drop 0.4 meters. How far away should the cup be? And again, you can't just use the simple range formula because it's not the range of an even trajectory, it's the range of an uneven trajectory. Okay? So let's see. So I wanted to use this as an example of how to solve an uneven trajectory. One way is to break it into two parts, the even part and the extra part. So the even part is that this will go through the path of an even trajectory. That just won't be the end of the problem. So if we start here, we're going to call this the origin. Where you start is usually the best place to make the origin. We're going to throw it up and it's going to make a parabolic trajectory to about there. So this is the even part. And then there'll be a second part where it goes into the cup. Okay? Let's do the even part first, because for the even part we can apply our standard kinematics formulas. So we can figure out this distance here. This is the range, according to the formula we would use. This is the height, which we're not going to need, and then, I don't think, and then there's the time it takes to finish this trajectory, which we may or may not need. So let's have a look. First, let's just calculate this range, the first part. So the range formula is 2 times the velocity squared times the sine of the angle times the cosine of the angle, sine of 60, cosine of 60, over g, okay, over 9.8. So this is just a formula we derived in class. It's one, maybe it's worth memorizing, it'll be on the equation sheet, but we've done the physics to get this formula, so I'm just going to use the formula. So if you plug those in correctly, 2v squared sine theta cosine theta over g, you get that the range is 0.795 meters. Okay, so part of the distance, 0.795 meters. But now the tricky part is how much farther does it go? So this is now a kinematics problem where, let's blow it up and think about it a little bit. We have an initial velocity, and we need to figure out how long is it in the air, and therefore how far does it get this way. Okay. So I think in class I talked about how which kinematics equation you use depends on what you need to know. In this case, we need to know a distance. Right? We need to know how far it goes. So we care about x equals x naught plus v x naught t plus 1/2 ax t squared. Right? And we're trying to find x basically from here to there, because we're going to add it to r. So what I would do on the second half is I would think of this as the origin. Instead of having to write x naught as 0.795, let's just call this the origin now. And that way x naught is 0, x equals 0 plus, and now what is vx naught going to be? Well, since this is an object freely moving through space or through the air with nothing pushing on it, it's true for the trajectory that the x component of the velocity is constant because there's no acceleration, and it's true as it falls through here. Nothing is pushing on it. It's just not an even part of the trajectory. So the Vx is the same as it was at the very beginning. It's 3 times the cosine of theta. So 3 times the cosine of 60. And then the acceleration of the x is 0. It's just smoothly gliding in the x plus that 0. And we need t. So what keeps us from having the answer right now is we don't know t. So this is a case where what we're looking for is in the x, but you often use the other direction to get information you need. Okay? So we're going to get t from the y motion. All right? So let's see. Well, to get t from the y motion, let's write out the whole thing for t. We could write this, or for y, we could write this for y. That's not quite what we want to do. Let's see. I think I found it was more successful to jump to the combo equation, the one vf squared equals vi squared plus 2ad. Because what we have in the y is we're accelerating for a known distance, 0.4 meters. We're not accelerating for a known time. So when you accelerate for distance, t from the y motion, accel for distance, right? That's the one where you say v final squared equals, and we'll say this is all y now, final y squared equals v initial y squared plus 2ad, that's the equation. So now let's plug everything in. The v final y squared is what we're looking for. Because once we get that final, we're going to be able to use g to figure out how long it took. But first, let's just get the final velocity here. And then v initial y squared. So that we could do the kinematics to find, but we actually know, because remember these things are even and symmetric. So what happens through an even trajectory is the x velocity stays the same, and the y one switches directions. It's driven from its initial value to 0 here, and in the same kind of trajectory in reverse, it's driven to the negative value. So it's really negative, and then it is, the y is 3 sine theta, 3 sine of 60 degrees. And that whole thing squared, so the negative doesn't matter. And then plus 2, the acceleration is negative 9.8. And the d, the distance, is what? Let's see, the distance is 0.4, but it's 0.4 down, right? It's negative 0.4, because we're going from 0 to negative, so negative 0.4. Okay, so what that's going to do is say we take this number, it's going to be positive because we squared it. This number is positive because we have 2 negatives there. And in the end, we get the final velocity in the y is 3.82 meters per second. Once you take the square root and everything. And technically, it's negative because it's down, right? It was initially down at negative 3 sine 60 degrees, and then it sped up because it accelerated, and it got up to minus 3.82. So the reason we did that is we needed to get a time. Remember, we only knew acceleration for a distance, so we used this formula. Now we have more information. Now we have the initial and final velocity, therefore we can get the time, because we know that v final in the y equals v initial in the y plus acceleration times time. And then we know how long this whole thing took, or this little drop took. So I'll stop writing all the numbers here. This is negative 3.82. This, if you get the number, is negative 2.6. So 3.82 minus 2.6 divided by minus 9.8, all the signs work out. And the time for this little chunk of the drop is 0.125 seconds. Okay, so this little part, all this, this whole thing was to figure out how long it took it to drop from there to there. Because when we know how long that took, we can now multiply that by this velocity. And we'll get that the extra x part is 3 cosine 60 degrees, and the cosine 60 is a half, right? So that's 1.5. 1.5 times 0.125. So this part of the x motion is 0.188 meters. 188 meters. And then we say, okay, 0.188 meters plus 0.795 meters. This total distance is the answer you want, 0.983 meters. So the question mark, 0.983 meters. And that was the answer.